So let's get started on the alternating series test. Of course, alternating series test is going to work for what type of series?
Alternating series.
Yes, obviously. So here's what a alternating series looks like, what it means. An alternating series is simply a series where sequential terms alternate signs. So positive, negative, positive, negative, positive, negative, positive, negative. That's what gives it this alternating. So it's a series where sequential terms alternate signs. No problem. Let me give you an example of what alternating series typically look like, and then I'll show you what the alternating series test is. So first, you have seen a couple of these before. They were very common in our sequences, actually. Now that we have a series, we're not just going to be alternating the signs, but we're going to be adding them together. So we had alternating sequences. We didn't really call them a name or anything. But here, alternating series, well, that's a specific section for us. So here's what they look like. Typically, there'll be some series, like this one. It's a horrible end. Some series like this one, and there will be something in it that makes the signs alternate. Do you remember what we had that made the signs of our sequences alternate?
Negative one.
That's right. To some power. Yeah, -1 to some power that was based on n. So for us, it's typically n minus 1. We usually, not all the time, we usually start with a positive term. So we usually start with, like, when I plug in 1, I would get 0, right? Remember how that matches typically? That's going to give us -1 to the 0 or 1. So we get a positive term to start with. That's normally how it happens. This is your first experience with an alternating series. So unlike the sequence where we just list them, the series is just going to add these things up. So here's what it would look like. What's the very first term? Don't want to plug in 1. 1, yeah. If you plugged in 1, you're going to get 1 over 1. It's going to be positive. You get 1. Would I add or subtract the next term? Because if I plug in 2, what's 2 minus 1?
1.
What's -1 to the first?
-1.
So I'd have minus 1/2. So whereas a sequence would just go 1, then comma, -1/2, then comma, positive 1/3, then comma, -1/4. What a series does, it goes, okay, 1 minus 1/2 plus 1/3 minus 1/4 plus 1. Are you guys getting the picture here?
Mm-hmm.
So the next one would be positive or plus 1/3 minus or -1/4 plus 1/5 minus, and it doesn't end. That's the way your alternating series will look. You okay with that?
Yeah.
Now, what's quite interesting is that this thing, any of these alternating series that do this, they can always be written as -1 to the n minus 1 times some other series where the a sub n is something that is always positive. So for instance, the only thing that's giving this the sign change is at -1 to the n minus 1. You guys agree with that?
Yeah.
Other than that, the 1 over n is the a sub n that we're talking about. So in our case, more specifically, this could be written as the alternating part, okay, this -1 to the n minus 1 times 1 over n. This would be our specific thing here. By the way, what type of series is that?
P.
No. Well, yeah, kind of. It's a specific type of p-series. I'm sorry, I said no, but you're right. It's a p-series with p equals 1, but we had a specific name for it. What was it? That's a harmonic series. So if that's the harmonic series, this is simply the alternating harmonic series, and that's literally exactly what that is. That's the, here, look at it. If that was a 1, that'd be the harmonic series. If I do this, it's now just the alternating harmonic series. Does it look familiar to you? It's alternating harmonic series. That's what it is. My point is that with any of these alternating series, you can always do this. You can always break off the -1 to your power and have some other a sub n, some other sequence that is positive terms. So hands if you're okay with that so far. Let me give you one more example. So right now we're not really working with them, we're just kind of getting the picture of what these things are. Like that one. Let's figure out a few terms here. Let's figure out a few terms there. So, what part of this is going to make our signs change? What part?
-1.
If I cover that up, do I have positive terms still?
Yeah.
Absolutely I do. So that's kind of interesting, right? So alternating series, we can break off that one part that makes it negative, we're going to have these positive terms. So let's figure out what the first few, let's do the first 4 terms this time. What's the first term? Let's figure that out. How much is this when I plug in 1? So our first term here is going to be negative. It said usually it starts off with positive. It doesn't have to all the time. So our first term is going to be negative. Now we'd have 1 squared, that's 1, over.
2 factorial.
So it's going to be 1, okay, so negative 1 over 2 factorial. Which of course is just 2, but I'm going to leave it as 2 factorial so we just keep the pattern, okay? I just wanted the first 4 to get the idea. Next one, everybody, am I going to get a plus or a minus?
Plus.
I'm going to get a plus, that's right, because this alternating series does that. The only thing that's changing signs is this negative 1 to the n. If I increase this to 2, then negative 1 squared is positive 1. I'd be adding. This becomes what? Over 3. Very good, and we can get the pattern really quick. So this will be, next week, so we have negative, then a plus, then a minus. What's going to go here? Here? 9. Over here. Let's do one last one. So negative plus, minus, plus, and then what?
16.
Sure, because we'd have the fourth term, 4 squared is 16 over 5 factorial. And then it doesn't end. It goes forever, never, never. Notice this. This is the same thing as some series where we have negative 1 to the n times a sub n, where a sub n is all positive terms. The only thing that's changing the sign here is that negative 1 to the n. Quick show of hands if you're okay with what the alternating series do. So alternating series is basically just having a negative 1 to some power that changes the signs, every other sign of sequential terms. Now, we do have what's called the alternating series test. Here's the test. It's really straightforward. It's not hard to do. It uses some things that we've already talked about in this class, so it's kind of nice. Here's the test for us. For an alternating series, so for some series, that's alternating. By the way, can you immediately tell that's going to be alternating series?
Yes.
Okay, this series, of course, if you wanted to write the first few terms, this would be a sub n minus a sub n plus, or a sub 1. A sub 1 minus a sub 2 plus a sub 3 minus blah, 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 all the way till we get to a sub n. Also, what I want to tell you is that a sub n itself, a sub n is positive terms. Does that make sense? The only thing that's making this negative is that negative 1 to a power. So a sub n is also positive. That's the idea. Are you sure you're okay with that?
Yeah.
The only thing that would be changing the sign would be the negative 1 to the n minus 1 in this case. Quick head nod if you're all right with that one. Okay, so what I'm telling you is that an alternating series has a negative 1 to a power times some other sequence that has positive terms. These would all be pluses if it weren't for the negative 1 to a power. Agreed? So that means that the a sub n itself is going to be positive. Cool. All right. So with this as our condition, if a sub n plus 1 is less than or equal to a sub n, what's that say? If a sub n plus 1 is less than or equal to a sub n, what's it tell you about the sequence from which we get our series? What's it telling you about that?
Decreasing.
It is, say it louder?
Decreasing.
It's decreasing. Can you explain why it's decreasing?
Because the next term is smaller than
That's exactly right. The next term is smaller. Do you guys understand? We did this like a couple times before, right? Do you understand this is the term right after this one?
Yeah.
If the term right after this one is smaller, that means that we are decreasing. So basically it says you're decreasing. So if this is true for all n, which means this is decreasing, and the limit as n approaches infinity is, oh, tell me something. This is gonna be good, right? This is usually the thing that I have you do. The first part of every single series we ever do, I have you do this. What does this have to be? Do you think?
0.
It's got to be 0. Now that's basically the divergence test. Now we don't really use the divergence test here because we don't include that -1 to n-1, but practically we do. We use it on a sub n. So this is the divergence test. So basically what we're saying is, hey, if your series passes the divergence test, so basically look at the sequence of positive terms. If your sequence of positive terms, when you take a limit as n approaching infinity, equals 0, and you know that the sequence of positive terms is decreasing for all n, if you know that, then you know that your alternating series is going to be convergent. This is the test.
It has to be decreasing?
Has to be decreasing. I'll show you why in just a second, okay? Let me recap this before I give you, I'm not going to prove this, I'll give you kind of like the graphical proof for it. It's a very common sense type of idea once you see it, okay? So let me do like a 20-second recap to give you everything about alternating series that you really need to know. First thing, alternating series alternates signs for sequential terms. It doesn't matter whether you start with a positive or negative. Typically we're going to start with a positive, but it doesn't really matter. What you need to know about these alternating series is they can always be broken up as -1 to some power times a sequence of positive terms. -1 to some power times a sequence of positive terms. Does that make sense? All you have to do for your alternating series test is first, verify it's alternating. Verify it has one of these things. Does that make sense? Verify that. If you can verify it's alternating, then all you got to do is look at the limit of your sequence of positive terms. Look at your a sub n. If the limit of a sub n equals 0, well, you know what? We do that anyway, don't we? That's the divergence test. So if the limit of a sub n equals 0 says, hey, you might not be divergent. If the sequence is also decreasing, so you look at the sequence of positive terms, if it's decreasing, which is what this says, then you know it's convergent. So all you got to show is that it passes the divergence test as far as the sequence of positive terms is concerned. Does that make sense to you? And that it's decreasing. Have we shown both those things in different times in this class?
Mm-hmm.
Lots, actually. We were often in the habit of showing decreasing. That was for monotonic bounded sequences. We showed that they were decreasing. We showed it for the integral test that was positive continuously decreasing. Now we're showing for alternating series. Just don't even worry about that, though. That's even part of it. Just look at your a sub n. If you can show your a sub n sequence is decreasing, man, you're good. If you can also show that the limit of a sub n as n approaches infinity is 0, that's the two parts of your test. We've done both. One's called the divergence test most of the time. One of them is just decreasing. If you can show both those things, then your series converges. Do you want to see why it converges? Okay, remember here that what we're doing is we're adding up numbers, right? We're adding up numbers that alternate signs, which means this. Are you listening? We're going to start with one number. We're going to subtract something, right?
Mm-hmm.
Then we're going to add something. Then we're going to subtract something, then we're going to add something. Then we're going to subtract something, then we're going to add something. Then we're going to subtract something, then we're going to add something. However, listen carefully. Here's the whole crux of this proof. If your series is decreasing, then you start with a number, correct? Let's assume it's positive. It doesn't have to be. It could be negative. But let's assume it's positive. If you subtract something, it's going to go backwards, right? But it's not going to go to 0 because what you're subtracting is smaller than what you originally have. Does that make sense? Now, you're going to add something to that, aren't you?
Mm-hmm.
But it's smaller than what you subtracted. Then you're going to subtract something that's smaller than what you added. and then back and forth. So practically, here's what it looks like. You start with, let's say we start with 0. Here's 0. After your first term, do you remember this? The partial sum with it was an S. We had that S sub n for a partial sum. So after your first term, you have a sum S sub 1, whatever that is. You're going to have some sum because you have one term. Make sense? Now, because we know that this is decreasing, you would subtract call it here, and get the sum 2. After 2 terms, that's what your sum would be. Do you understand that it would have to be positive here? If I start with a positive number, I'm going to subtract something that's smaller than that positive number. True? Now, I'm going to add something. Is it going to make it all the way back over to here?
No.
No, it's got to be smaller than that because whatever I'm adding for my third term is going to be less than whatever I subtracted for my second. And we keep on going. Because I'm decreasing, I'm going to get closer and closer together. Do you see that ultimately what's going to happen? I've lost my arrows, didn't I? So this way, this way, this way, this way, this way. Ultimately, what's going to happen is that I'm kind of doing this ping pong match. If you ever watch someone playing tennis, right? What you start here and you volley the ball over, and some guy runs up and hits it. Let's pretend that these two guys start at the end of the court, and this guy hits the ball here, and then he hits it back, but doesn't go to the end, and he hits it back, but it gets closer, and he gets closer and closer and closer to the net. And these guys are coming up and going like that. And every time you hit the ball, the guy steps forward a little bit. Does that make sense? They're going to get really close to something. That's what this is doing. It's saying, okay, you're adding, you start with one term, then you're subtracting something less than that, adding something less than that, subtracting something less than that, adding something less than that. It's going to get really, really close to one sum. Remember that the sums are what we're going to. We're not adding all the rest of these things together. These are the sums. Because you're subtracting numbers and adding numbers back and forth. So sum number 1, hey, subtract it. Sum number 2, add it. Sum number 3, subtract it. Sum number 4. Because we're decreasing, eventually I'm going to start adding and subtracting numbers which are so small they don't make a difference at infinity. Show of hands if that makes sense to you. And that's the idea of proving that this is convergent. Because it passes the divergence test, and because we're decreasing, and because it's alternating series says, yeah, you're adding and you're subtracting, sure, but you're decreasing, right? So what you're adding and subtracting keeps getting smaller and smaller and smaller and smaller and smaller. Therefore, we're going to get really, 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 really close to one number eventually at term infinity. At term infinity, S sub infinity. That'd be the limit of S sub n as n approaches infinity. Hey, we did that. We did a limit of partial sums as n approaches infinity. That would be one number. That's the idea. Have I explained that well enough for you guys to understand the basis of this test? Are you sure? I don't want to leave anybody hanging on this one. Is it clear for you? The whole adding and subtracting, then adding something smaller, subtracting, eventually you're going to get down to one number. Now, let's go ahead and show how this actually works, okay? I'm actually going to start with this example. Are there any questions on this other one? So let's show what this one does. First things first. What must we show all the time, every time, for all our series ever, basically? Oh, okay. Doesn't necessarily have to be positive all the time. Continuity would be for the integral test. You're on the right track for integral test for sure, okay? As far as every series ever, what do we always check first? The divergence test. So let's do that first. So I know these are kind of out of order, but I'm going to always show this one first, because if I can show this one doesn't work, I can just stop. So number 1, we're going to take a limit as n approaches infinity of a sub n. Now please listen carefully. When you do your limits and when you check for decreasing, please look up here for right now. Look at this. When you do that, is negative 1 to the n minus 1 part of your a sub n? No. So basically, we ignore it. That just says it's alternating. So right here we go, okay, you're alternating. Now look at this, the rest of your series. That is your a sub n. So when I'm looking at this one right here, when I'm looking at this one, what part says it's alternating?
The negative.
Take that part away. I'll put a little side note here for you. Recall, a sub n in this case is 1 over n. It does not include the negative 1 to a power. That's why I made such a point about you can always pull out the alternating part, and you can always have a series of positive terms, or a sequence of positive terms, that a sub n. Show of hands if you understand that concept. Okay, so do we need the negative 1, oops, I kind of reset with my palm here. Do we need this negative 1 to the n minus 1 inside my limit?
No.
No, absolutely not. All we've got to do is, this is what it says, folks. It says the limit of a sub n, not the limit of the whole thing. Who cares? It's just this little piece right there. Show it's decreasing. Well, that's just the a sub n, not this piece. Who cares? We just want to show that the sequence is actually decreasing. That's the idea. So for us, I'm going to write this down a little bit. Let's take a limit of, so practically what you do, cover that up, write the rest of it. What's that going to be?
1 over n.
Tell me, what's the limit of 1 over n as n approaches infinity?
0.
Does that pass our version of the divergence test for this?
Yes.
I say our version of the divergence test because we're not really taking the limit of the whole thing. It's just the sequence of positive terms. That's what we're taking the limit of. So it's kind of our version of it for this. So check. That's brilliant. What's the next thing that we should do? We've got to show it's decreasing. So this is a two-part test. It's do the version of the divergence test, and then secondly, show that this thing is actually decreasing. So number 2. How in the world do we do that? You could. You could do it a couple ways. It's probably, and sometimes we're going to be using the derivative. Remember the derivative idea to show decreasing?
Yeah.
You call this thing a function. You take a derivative, and if the derivative is negative, then the function is decreasing. No problem. Well, we can do that, or sometimes it becomes a little bit, just a little easier. For instance, here's what I would say. Because it's so fast for this one, here's how I would do it. I'm going to move up so because I need a little room. A sub n plus 1 is equal to 1 over n plus 1, correct? You know, I just asked correct, but do you see where that's coming from? A sub n plus 1 says, hey, you plug in n plus 1. Is that less than or equal to 1 over n? For all n that are positive.
Yes.
And is this equal to a sub n? Sometimes it's easier to do this than it is a derivative. So right now this says that a sub n plus 1 is less than or equal to a sub n. That shows that it is decreasing.
What about the fact that it's a harmonic series?
Okay, we're going to talk about that right now. I want to make sure that this is okay with you, all right? Do you understand that this is an alternating series? Hello, yes, no?
Yes.
What says it? Alternating. Are you okay that the limit of the sequence from which our series is built as far as a sub n is concerned is equal to 0? Yes. Convergence test. Are you okay that this sequence is also decreasing?
Yes.
So, a sub n was 1 over n. We showed that the limit of that sequence is 0. Satisfied that part. We also showed that this thing is decreasing because, well, if I add 1 to this, I have 1 over n plus 1. That's always less than 1 over n for all n greater than 1. Brilliant. Okay. Well, that's equal to a sub n. So now I've shown that a sub n plus 1 is less than a sub n. That said that's decreasing, so I satisfied this. By the alternating series test, we have something that's alternating. We have something where the limit of our sequence is 0. We have something that is decreasing. Tell me something about this series. It converges. It converges. So read this way. So, by the alternating series test, yes, you have to state what you're using here. There's going to be a lot of freaking tests. Okay, so state what you're using. By alternating series test, because it passed the divergence test, because our sequence was decreasing, we know that by the alternating series test, the series of -1, n minus 1 over n converges. Okay, honestly, that is the entire lesson. That's the whole idea. There's only one alternating series test, there's only one thing you do with it, and that's it. Did that make sense to you? Now, of course, we're going to do a few more examples, sure, but this is practically the idea. Show of hands if you feel okay with the idea. Now, this is what's really interesting. If I take this away, if I look at this series, what is that series? Harmonic series. Tell me something about the harmonic series. Diverges. This is called the alternating harmonic series. Do you see why it's called the alternating harmonic series? It is a harmonic series, only it's alternating. The alternating harmonic series is actually convergent, and that's weird. So the harmonic series diverges, yet the alternating harmonic series converges. It can be confusing, so make sure you mind your P's and Q's, or harmonic series and alternating harmonic series. This is the alternating harmonic series. And yes, it converges. Now, fortunately for us, we don't really base anything on the alternating harmonic series. We don't say that, oh, this is always less than our alternating harmonic series. We don't really do that. And so all of these are kind of made from scratch anyway, so you don't necessarily have to remember that. I would like you to, because it's important. We will use it eventually. But you can always redo it, okay, with the alternating series test. We use the harmonic series a lot because we're always doing, well, it's kind of like a p-series. So you could just think of it as a p-series, but we always compare things to it a lot. So that's kind of nice to know. Let's continue. Tell me something about this series, please. What do you see right off the bat that says this is this type of series? It's alternating. How do you know it's alternating? Very good. So we know it's alternating. What are we going to use for alternating series? Probably the alternating series test, because it's an alternating series. Yeah, and that's the easiest test we have for this, okay? Show it's decreasing. Show the limit of a sub n is 0. Can you tell me what is a sub n in this case?
2 and over 4 and minus 1.
Yeah, that's exactly right. It's not hard to do. Now, what would you do first if I gave this to you on a test? Would you show it's decreasing first, or would you show the divergence test first? What would you do?
Divergence.
I would do that first. Why?
Because
Because it's easy. It's easier, okay? So even if we were to show, I'll show it's decreasing here real quick, by the way. In this case, it's a lot easier to show with a function, with a derivative, than it is by showing it directly like this one. This is why I give this example. This sometimes is hard to do. Sometimes it's really easy, like this was easy. But if I wanted to show that 2n plus 1 over 4n plus 1 minus 1 is less than or equal to 2n over 4n minus 1, I might run into some trouble. Okay, it's just harder to do. It's harder to actually show that. Does that make sense? So rather than do that, I'd be like, nah, I don't think so. I would think of f of x equals 2x over 4x minus 1. I would find a derivative of that thing. By the way, all of this is kind of a moot point. Do you understand that? Do you understand that when I take the limit of this, it's going to equal 1/2?
Yes.
And that's not 0, therefore this thing will diverge by the alternating series test, by the divergence test. But I'm just showing you something extra right now, okay? So if you didn't show it like this, you could show it with a derivative. It would be low d high minus high d low, and square the bottom.
No way we go.
Away we go. I think if I did it right, looks like I did. Did you get that too? If you did it? -2 over a bunch of junk?
Yes.
So, is this thing always negative? What do you think?
Yes.
Is this thing always positive?
Yes.
Is this always negative?
Yes.
Negative over positive is a?
Negative.
So this is less than 0 always. Therefore, if that's always less than 0, what's it tell you?
It's decreasing.
It's decreasing. This is a slope, yes?
Yes.
The slope is
Negative.
negative. A slope that's negative says that your function is decreasing. Since our function is modeling our sequence for us, it says that our sequence is also decreasing. I'll say that one more time because I'm sure it didn't sink in. Some of you aren't even looking at me. Man, goodness, people in the video, they're watching me. You should watch me too. So
They're probably texting.
they probably are texting. Stop texting. Anyway, so if this is a derivative, it means a slope. If the slope is negative, which it always is, that means that the function is decreasing. Since this function contains every point of our sequence is also decreasing for anything n greater than 1. No problem. So this says decreasing. Would that be good for convergence as far as our alternating series test is concerned? Would that be good for us?
Yes.
Yeah, that would have to be decreasing. So that fits half of it. Now, of course, what we would have done first, this is number 1, we do a limit of 2n over 4n minus 1 as n approaches infinity, and we would get 1/2. By whatever you want to do with that, you're going to get 1/2. Show of hands if you feel okay with that one. What's that say?
It's divergent.
This is not 0. In practicality, if you were doing this problem on a test, you would not even get to this. You'd say, let's do a limit first. Let's do the limit of this guy. The limit of this guy is, 1/2. Is that equal to 0? By the alternating series test, by the divergence test? Series diverges. You wouldn't even make it to that. Why would you do extra work when this already tells you that it diverges? Show of hands if that made sense to you. Okay, so yeah, it decreases, but it's not just about decreasing. Okay, both of these things have to work in concert to give you a convergent series. Understood? Let's keep going. Really, we're only going to do one more, and then we're done. We're done with this because it's all the same. It's all the same stuff. By the way, do you have questions on that? Forgot this one. Now, of course, just because it's all the same doesn't mean everything's super easy all the time. I mean, you just have to show
Bless
stuff.
you.
Bless you. You gotta show stuff. So let's start with this. You're given this problem on the test. What do?
You check.
Panic, pee your pants, run out of class. I never learned any of this! Seriously, it honestly happened in class one time. It was a
What?
final, yeah. Person stood up, I don't remember any of this crap! Threw his test down and walked out. It was awesome. Not in my class, in someone else's class. But that
Did
was,
they pass? You know?
no, they failed miserably. It was a final. Anyway, so what do you do? What do you do on this?
Check what kind of series it is.
What kind of series is it?
Alternating series.
What are you going to use for alternating series?
Alternating series.
Now, yeah, I'm going to give you a couple other tests that do work for alternating series, okay? So for right now, that's all you got. I will give you some that are sometimes nicer, and we're going to see when they're nicer when we get there, all right? Specifically, we're going to have things like factorials, stuff like that, where this would be very hard to show with factorials, possibly because, well, we're going to take a derivative. Do you know how to do derivatives of factorials? No, we don't. So we can show it with other techniques as well. But right now, if it's alternating series, use alternating series test. What are you going to do first, ladies and gentlemen? Okay, let's look at a sub n. What is our a sub n in our case?
Square root of n plus 1 over n minus 1.
Okay, now what? Would you do decreasing or limit first?
Limit.
Do limit. Do limit first then.
Oh, so here's a limit.
How would you show this limit? How would you do it? There's two ways that I can think of right now. How would you do it?
Pull out into the 1/2 on top and do the limit.
What do you mean?
Well, yeah.
He says,
Divide it by n.
he says,
You could divide everything by n. That would be one option. Can't do that. Oh yeah, you could actually. You could do numerator, denominator. Not going to help us all that much, but I like where you're at. You would use that if you had a conjugate. If you had to use a conjugate. You might try L'Hopital's. Sure. Could you do L'Hopital's?
it's okay.
Yeah, why not? You could do that. I don't know if both are going to work. The only one I would see is divide by n. That's what I would do. If you did L'Hopital's, let's see. Do you understand why we can use L'Hopital's right now, everybody?
Infinity over infinity.
That's right. L'Hopital's might actually be pretty nice, because what's the derivative of n minus 1? I like getting ones on denominators. Don't know about you guys, but that's kind of nice, right? This gives you 1/2. Actually, you know what? Also, no, to make it nice. This would give you 1 over 2 square root n plus 1. Can you verify that for me to make sure I didn't do a mistake?
That's right.
But if you do it, remember that this is n plus 1 to the 1/2. So a L'Hopital would do 1/2 n plus 1 to the negative 1/2. That's over a square root. So this would be a, if I did a derivative, you'd get the, here's the 1/2, here's the n plus 1 to the negative 1/2.
Uh-huh.
Now, let that go to infinity. What's n as n approaching infinity?
Infinity.
Plus 1?
Infinity.
Square root?
Infinity.
Times 2.
Infinity.
1 over infinity.
0.
0 over 1.
0.
Does it pass the divergence test as it's concerned for alternating series?
Yes.
Could you have done as Aaron suggested and divide everything by n?
Yes.
Be careful on this. If you divide everything by n, watch your square root. What happens is you do this, n plus 1 over n, n minus 1 over, sorry. Like that, you know?
Uh-huh.
True? Kind of true. This, remember, all these would have to be equal, correct? This does not always equal this. That is not true all the time. This always equals that. That is true all the time. You need to be careful on that. Now, of course, why are we unconcerned? Where does n start?
1.
And it goes to, so it's always positive. So for that case, it doesn't really matter. But if you would have n go into negative infinity, just in case you ever get a limit where n goes to negative infinity, that changes to a negative n. Are you all clear on that? So
Yeah.
just be careful. Yeah, you can do it because n's going to positive infinity. Yeah, you're good, okay? This is absolutely true, but this is really the definition of it. Okay, anyway, in either case that you would get 0. So let's backtrack a bit. The first thing you do is you test a limit. That's basically like the divergence test for alternating series. Did it pass?
Yes.
So should I stop or keep going?
Keep going.
Does it say that we're convergent right now?
No.
Not yet, but we're halfway there. Possibly. Possibly convergent. Number 2, what's number 2?
Show decreasing.
Tell you what, trying to show this is less than or greater than n plus 1 in a square root over n plus 1 minus 1 can be tricky. What might we want to do instead of that?
Derivative.
Let's do a derivative. So here's how you do the derivative. You say, okay, let's pretend this thing is a function of x. And get, by the way, do I want to include this in my derivative?
No.
Heck no. I want x plus 1 over x minus 1. That's what I want to do. So let's take a derivative of that guy. So, oh man. Low d high minus high d low square the bottom, and away we go. Correct me if I'm wrong. If you see any mistakes, please do that. I'm just going to do it kind of quickly. Oh, goodness. That's nasty. What would you do? Did you get that far, by the way?
Yeah.
What would you do now? Give up. Simplify. Yeah. Get a common denominator. Combine your numerators. It's complex fraction right now, which sucks. Complex fractions always say get one fraction on the numerator, one fraction on the denominator, and go for it. So in our case, we get, let's see, x minus 1 minus 2 times x plus 1 all over 2 square root of x plus 1 over x minus 1 squared. At least I believe so. I'm kind of doing it quick in my head, but you'd have to multiply by 2 root x plus 1 over x over 2 root x plus 1. And that would give you this. Still okay so far?
Yeah.
Let's keep on rolling. So we'd have f prime of x equals, what do we get on that numerator? Looks to me like it's negative x minus 3. Did you get that? Negative x minus 3?
Yeah.
Negative x minus 3 all over, if you do all of this, you're going to end up with 2 square root of x plus 1 times x minus 1 squared. Go no further because we're not trying to figure out a limit. So don't think, oh man, we got to do a limit. We got to get rid of the x on the numerator. Who cares about that? All we're trying to see is whether this is positive all the time or negative all the time. Are you with me? Are you listening?
Yes.
It's a derivative, right?
Yeah.
Derivative gives you increasing versus decreasing. So we make it this far. Make it to one fraction, then look at your fraction. Is that positive?
Yes.
Is this always positive?
Yes.
Is this always positive?
Yes.
So your denominator is always positive. Your numerator. Is your numerator always positive?
No.
It's always,
Negative.
if x is greater than 1, yes, absolutely. Because if x is 1, you get negative 1. If x is 2, you get negative 2. X is 3, you're going to get negative whatever you plug in. Does that make sense? That means that this is always less than 0 for x greater than or equal to 1. And here's where we make the jump. We've done this several times. I'm going to do it one more time. This function is modeling our sequence right now, which means that every term of our sequence will be somewhere on our function. Do you get that? This includes way more points than this will ever have. Since this function is always decreasing, we prove that by taking a derivative. The derivative is always negative. A negative derivative says that your function is decreasing. That's what it says. So since our slope's negative, function's decreasing. Since it's decreasing for every x greater than or equal to 1, that means that because a sequence fits in here, the sequence is also decreasing for every n greater than or equal to 1. Show of hands if you understand that concept. Therefore, this says a sub n is decreasing. Let's put it all together. All of it right now. Do we have an alternating series?
Yes.
We use an alternating series test. So this says alternating. We look at our sequence. Does the limit of our sequence from which our alternating series is built, does that limit as n approaches infinity equals 0?
Yes.
That passes the divergence part of this test. Then we do the second one. Is the sequence from which our alternating series is built also decreasing everywhere?
Yes.
So alternating series test says if it's alternating, if it passes the divergence test, if it's decreasing, those three things, what do you know about this given series? So, by alternating series test, or AST, the given series that we have converges. By the way, if you notice something, we kind of set this for n greater than or equal to 1. Yeah, we can't really have it equal to 1. You pick 2. Pick something like that. Now, if we said 2, is it going to make a difference?
No.
Or equal to 2? No, as a matter of fact, our series didn't even start till 2, but even if those numbers didn't work out, please recall that you can add or subtract a finite number of terms from your series, and you still have the same convergence or divergence. Does that make sense to you? So it doesn't even matter if they don't really match up. Yeah, your sum would be different, but because we have this series idea of convergence or divergence rather than find the sum, we're okay. Did today make sense for you? All right, so the last little bit of this, talking about alternating series. Now here's the deal. Have you ever wondered if a series goes forever and has a sum, and we can't add forever, how in the world can we say the sum of a series is what it is? Well, the limit idea lets us know that, but if you understand this about the series, if I add a finite number of terms, there will be some sort of difference between the sum of the series and the sum that I have. Does that make sense? In other words, there's going to be some sort of error. Well, let's talk a little bit about finding error on our series. Here's what we know. If your series converges, then it will have some sum. Let's call it S. And we also know this. This is old stuff. We also know if we take a limit of partial sums as n approaches infinity, then the limit of partial sums will equal that sum S. Let me explain that with some different notation. So if I take a limit of S sub n, do you recognize that notation S sub n? S sub n was a partial sum. It said, hey, find the sum after n terms, find the sum after 5 terms, after 10 terms, after n terms as n approaches infinity. And this was our very first kind of an idea for finding the sum of a series. It said, tell me what a partial sum is, then let n go to infinity, because if n goes to infinity, the limit of partial sums as n approaches infinity will equal the sum of the series. That was the whole idea. This is old stuff. Do you recognize the old stuff? If you need to brush up, it's in one of the first sections on series. I think it was like 4 sessions ago. So this is what that said. It said, hey, take a partial sum, no problem, let n go to infinity, then that partial sum will equal the sum of our series. Old stuff. Well, if this is true, if the limit of partial sums as n approaches infinity equals S, then the difference between these things will equal what as n approaches infinity? If these things are equal as n approaches infinity, what's the difference between them?
It should be 0.
It should be, and it is. Does that make sense to you? If the limit of S sub n as n approaches infinity is S, then the difference between them would be 0 as n approaches infinity. As n approaches infinity. You guys okay with that so far? Now, I made a statement as n approaches infinity. So what would happen if n doesn't get to infinity? If we don't have this statement. So if we don't actually get to infinity, is this still going to be 0? No, there will be some error. Let me write that down for you so you have a little bit of note. So now, if n doesn't actually approach infinity, there's going to be some difference between S sub n and S. Does that make sense? If we don't actually get to infinity. Now, we kind of usually can't get to infinity. We have this definition of a limit saying n approaches infinity. But if we don't actually get there, there's going to be a difference between S sub n and S. We call that difference error. Or we have a special name for it. We call it R sub n. You guys get the idea here? I'm going to write down so you're hopefully still with me. So, if n does not approach infinity, or in other words, it never makes it, okay? So if we stop somewhere along the way. If n does not approach infinity, or doesn't actually get there, there will be some error between s and s sub n. We call that error r sub n. Okay, let me recap just a little bit, okay? So here's the idea. The idea is, yeah, if a series converges, it's got to have a sum. No problem. This would be true as well. If we take a limit of our partial sums as n approaches infinity, we say, yeah, go to infinity. Guess what? The limit of your partial sums is going to equal the sum of your series. No problem. We had that last time. Well, we had this several times ago. And we also say, if I subtract these two, yeah, the limit would equal 0 if n goes to infinity. Now, assume that n stops before infinity. It goes for a long, long way, but it stops before infinity. This is no longer true because I don't have this idea of a limit. I don't have the idea of n going to infinity. Does that make sense to you? I have, okay, we're stopping somewhere. Well, then the partial sum is probably going to be, let's say we do the first 1,000 terms, okay? The partial sum's probably going to be really close to that sum of the series. It's going to be really, really close. But it's not going to be exact because we didn't get to infinity. Does that make sense to you? So if we, now, this is what I'm saying here. Now say n doesn't approach infinity. Okay, stop somewhere. There's going to be some error. It's going to be really close, but there's going to be some error. Show of hands if that made sense. Feel okay? Okay. So here's what we know. Since there will be some error between these, if I take s minus s sub n, this is what we're calling r sub n. Basically, it means this, and hopefully this makes sense. R sub n stands for your error. That's what it is. So this says that your error is equal to, what's S stand for? Sum of?
Partial sum.
No, that's S sub n.
That stands for the sum of the series. That's what we said. Sum of the series, sum. So this would be like the idea of the whole sum, the sum of the series, the whole thing. So the whole sum minus part of the sum. That's a partial sum, part of the sum. So we have, okay, if we don't go to infinity, there's going to be a difference between these guys. Make sense? We call that difference r sub n. Naturally, it would say the error is equal to, well, does that make sense to you, the notation? Well, this is error, right? It says take the whole thing, subtract off part of it, that gives you the difference between them, that gives you the error. So we have error equals whole sum minus part of sum. It's a very wholesome idea that we have going on. Oh, man. Now, the following is for alternating series only, and you'll see why. I'll explain why in just a moment, why it's for alternating series only. This idea, okay, we have this, but now we're going to apply it to our alternating series, why we're in this section now. So for alternating series only. For alternating series only, we have the following idea. It's very interesting. I'll explain why after I put it on the board here. This is kind of cool. Check it out. We know this is true. Error equals the whole minus the part. True? Mm-hmm. Now, because we're dealing with alternating series, this right here could be positive or negative, right? Could be. Well, actually, this could be positive or negative. We're going to make this absolute value because of the next thing we're going to do. Here's what I know, and this is the interesting part of this. Hopefully you believe this, true? You believe that already? Yes, no?
Yes.
Here's what I know. This error is always going to be less than or equal to a sub n plus 1. Always. Now, some of you are probably thinking, oh yeah, that makes sense. Some of you are like, what in the world are you even talking about? A sub n plus 1, think about this for a second. S sub n would be the sum when you stop. The sum when you stop at the nth term. Does that make sense? It says, go a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, a sub n, and add them all together. That's what this is. S stands for the whole thing. What I'm saying is that this difference is less than or equal to the next term after you have stopped. So you do a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub n. The next one would be a sub n plus 1, right? If you add all this up and you subtract it from s, that difference is less than the next term. You go, why in the world is that? We'll talk about it right now. Here's the why. Let's consider what s is. S would be a sub 1. Remember, this is alternating, and the reason why this only works for alternating, I'll show in a reason, okay? But this is an alternating series. I'll show in just a minute why the reason is. This is an alternating series, so it'd be a sub 1, a sub 2, a sub 3, blah, 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 blah. And eventually you get a sub n. True? Now, would S stop there?
Yes.
No.
S would go forever. S never stops. So S would do n plus 1 minus a sub n plus 2 plus, and it would go forever and ever and ever and ever and ever and ever and ever and ever. Does that make sense to you? Now here's the deal. This is all of S. So this is the whole thing. I'm going to write it a little differently. This whole thing is S. Does that make sense? Can you find S sub n somewhere in that series? You have to be, right? Because S sub n is a partial sum. It's part of that sum. So it's got to be in there somewhere. Where does S sub n stop?
A sub a sub n.
That's S sub n. Does that make sense? Hello, yes, no?
Yes.
Now, here's the cool part. The rest of this, by definition here, would have to be S after I take away S sub n. Does that make sense to you? Hey, look it. If the whole thing's S, and this first part is S sub n, then the rest of it is S minus S sub n. That's what the rest of it is. Now understand something about why alternating series plays a part of this. Check out what the terms do. The next term after this is a sub n plus 1, correct? Now I'm assuming that's going to be a plus. It doesn't have to be. That's why we have the absolute value. I don't care what it is. It's absolute value. So I have that a sub n plus 1. Let's assume it's positive. What's the next thing I'm doing?
Subtracting.
I'm subtracting from it. I'm making it smaller, aren't I? Now, understand that with alternating series like this, we have this idea that it's decreasing, okay? We have the idea that it's decreasing because it's convergent. Alternating series that are convergent, this would have to be the case. It would have to be decreasing. It would have to have the limit of your sequence being 0, and it would have to be alternating. So we're already stating this is convergent. Does that make sense to you? This is not an alternating series that increases. Otherwise, this wouldn't even happen. Does that make sense? So am I talking over your heads here, or are you guys with me? I hope you're with me. I want you to be with me here. So if it's convergent and it's an alternating series, then it must be a decreasing sequence. A sub n must be decreasing. What that means, as far as a convergent alternating series, why this is important is because if we have this as S minus S sub n, here's my first term after A sub n, my very first one. Do you understand that if something's decreasing, every term will be less than that in absolute value? It's going to be less than that. So I'm subtracting, that made it smaller. I'm adding, it made it bigger, but since I'm adding something smaller than what I subtracted in terms of absolute value, it's never going to make it back to what a sub n plus 1 is. Does that make sense? Start with any number, like 10. Subtract something from it, like 9, add something smaller than that, like 8. Are you ever going to make it back to 10?
No.
No. That's what the idea of a decreasing, convergent, alternating series has to do with this. It says alternating is important because I'm not continually adding, I'm subtracting, then adding, then subtracting, then adding, then subtracting, then adding. I'm never going to make it back to the 10 because my sequence of terms is decreasing. Show of hands if that makes sense. Well, if that's the case, then what we know is that this whole thing must be less than or equal to a sub n plus 1. And that's exactly what we're getting right here. That's the whole idea. I'm going to write that. Hopefully you guys can see it a little bit clearer. So this is s minus s sub n. It must be less than, because it's decreasing, because we're alternating a sub n plus 1. And that's exactly what we have. We say r sub n is defined as the difference between this and this. So basically this guy. This is my error. This is my error. It's the difference between my sum and my partial sum. This is the error. Because that error has to be less than my very first term after I stop my partial sum, we have this as our definition for our error. Did I explain that well enough for you guys to understand it? Okay. Let me show you how it works in practicality. Do you have any questions on any of this stuff? Because I'm going to erase this and start my example over here. Are we good? Okay. So let's start with an example, and I'll show you where the error comes into play. Let's do a series like this. You know, if we're going to talk about finding error, we better make sure that we have a convergent series. It really wouldn't make a whole lot of sense to find error if we didn't know that this was a convergent series. Would that make sense? Because if this thing adds to infinity, well, how are we going to find the error? That doesn't even work. So, by the way, finding error only works for convergent alternating series, so we're going to have to make sure that this thing actually converges. Does that converge? Don't just guess at it. Have we shown anything about it? Okay, so you tell me how I show that it actually does converge. Divergence has to be first. Firstly, actually before that, tell me what type of series this is. Alternating. So with an alternating series, you might want to use the alternating series test as 2 parts. Alternating series says, does it pass the divergence test for alternating series? So basically, by the way, what is your a sub n here? Do you know what your a sub n is?
1 over n factorial.
Yeah, just cover that up. So the alternating series test says, number 1, I want to find a limit of a sub n. Everybody, what does that have to be in order to continue and say it's not necessarily divergent?
0.
Is it?
Yeah.
So that passes the first part of my alternating series test. It equals 0. It's like the divergence test for alternating series. Number 2, what's the next thing we've got to show for alternating series past the limit of your sequence equals 0? Decreasing. Why is decreasing important? Because it's alternating. If you keep going back and forth, plus, your terms get bigger, it's not going to work. But if your terms get smaller, remember that whole sum idea? We went forward, then back, eventually we're going to once. And we wouldn't even be able to find error if it wasn't decreasing. So, yeah, it's got to be decreasing. Is it decreasing? Would you show decreasing here with a derivative?
No.
Why not?
We can't even take a derivative of
Factorial, okay, so we'd start with a sub n plus 1. We'd show that a sub n plus 1 is greater than or less than a sub n. You want this to always be going less than the next one. So we want to show that this is ultimately less than or equal to a sub n. How much is a sub n plus 1? You know how to find the next term? You start with whatever a sub n is. Look, it already gives you a sub n. And then you just add 1 to however many n's you got. So for us it'd be 1 over n plus 1.
Factorial.
Yep, n plus 1 factorial. Does that make sense to you? Is it true, and by the way, here's a sub n, right? A sub n is 1 over n factorial. Is it true that this is less than or equal to this?
Yes.
then we've proven that a sub n plus 1 is less than a sub n. And that's a second part of our alternating series test. That says that this thing is decreasing. Show of hands if that made sense to you. This is old stuff. So what we would say is, by the alternating series test, yes, you have to tell me what test you're using. By the alternating series test, because our sequence a sub n, the limit of that is n approaching infinity equals 0. That passes that divergence test. Because our next term is less than our previous term, that shows that we're decreasing. By alternating series test and these two conditions, we know that the series that we have started with, our given series, does what? That's right. If the series converges, this is our condition, if the series converges, there will be some error between a partial sum and the sum of the series. So you have to show it converges first before you start doing this nonsense, because otherwise this does not matter. Does that make sense to you? So we'll go, all right, well, it converges. Therefore, between any partial sum and the sum of the series, there will be some sort of an error. Now, here's how you use the error. You ever wondered, well, what's the point of doing some of this? Because, yeah, we know it converges, but we still can't find the sum. So why are we doing it? Well, we can find the sum to a close enough value for us. And this is how we do it with an alternating series, at least. What do you do with the error? What you do with the error? You tell the series how accurate you want to be, then you find the number of terms it takes to be that accurate. Some of you are looking at one. Sounds like a riddle. Yes, well, I'll explain that in just a second. Let's start with what we know. What we know is that there's going to be some sort of an error. And we know that that error will be the difference between the sum and the partial sum in terms of absolute value. And we also know that this will be less than a sub n plus 1. Does that make sense? Hello, yes, no?
Yes.
Okay. Now, do you have an expression for a sub n plus 1?
Yes.
Yes, you do. In fact, we just had it. If you didn't, you could make it easily. You look right here and you just do n plus 1. So for us, we know that this is the same thing as 1 over n plus 1 factorial. You okay with that?
Mm-hmm.
Okay, so practically speaking, we know that r sub n must be less than or equal to 1 over n plus 1 factorial. Now again, here's the way that the error works. Do you want me to write this down? Maybe I should write this down for you. Here's the way the error works. You tell the series, the partial sum, you tell the series how accurate you want to be, and then you use the error, whatever this is, to tell you how many terms you need to be that accurate. You tell it. So, how the error works, you tell the series how accurate you want to be. Then you use r sub n to determine the error, to determine how many terms are needed to be that accurate. Let me give you an idea. So, firstly, are you okay getting down this far? Quick hand if you're okay with that. So here's the way that we go from here. Somewhere along the way, you're going to get a number, like 0.0005 or 0.0001 or something like that. And I'm going to give this to you on a test, or your homework's going to give it to you and say, tell you what, I want you to find the partial sum such that, so example, such that I want R sub n in terms of absolute value to be less than or equal to 0.0005. Now, please don't just do this by rote memorization of how you do a process like an algorithm, okay? Understand what this says. What this really says is, I want you to get the difference between the sum and the partial sum to be less than 0.0, actually let's just do strictly less than 0.0005. I want the error to be less than 0.0005. So what that means is that I want you to give me the term so that when I do that amount and I add my partial sum, that it's going to be less than this much difference from the sum of my series. Are you catching that? Say it one more time so it really hopefully sinks in. What this says is that I want you to tell me how many terms I need so that when I add them all up, this is the difference. The difference between my partial sum, which you just added, and the sum of the series, the whole thing, is less than 0.0005. That would be tenths, hundredths, up to the 5/10,000ths. So it would be very, very close. Now the reason why we have absolute value, this could be, the partial sum could be a little over it, or it could be a little under it, but it will be within 5/10,000ths of that. That's pretty darn accurate. Does that make sense to you? Okay, so here's what we do. We go, right, well, cool. Well, tell you what. We know that R sub n has to be less than this, right? So, and we want R sub n to definitely be less than this. So here's what we do. We go, if R sub n has to be less than this, if we make our last term less than 0.0005, would that not fit the condition of R sub n being less than that? Hope I didn't blow your minds. I see some wheels turning here. What? What's happened to this? Okay, here, check it out. You're given an error, right? Your error has to be less than 0.0005. In this case, where did that come from? I made it up. It's going to be given to you. Or you come up with it on your own later on, whatever. So I want my error to be less than this. Well, if my last term, I make my last term less than 0.0005. I know for a fact R sub n is less than my last term. So if I make my last term less than this number, whatever my error is, then R sub n for sure is going to be less than that. Because this is less than this is less than that. Bam. So set your last, this is as easy as this, set your last term, your actually your next term. A sub n plus 1, set that less than your error. Solve for n. Done. Now, how we solve for n can get exciting. Did you know that if you take a reciprocal of an inequality, your inequality just reverses? Did you know that?
Mm-hmm.
So then I do n plus 1 factorial is greater than 1 over 0.0005. Can you tell me how much is 1 over 0.0005?
2,000.
It's 2,000. That's right. You guys okay with where the 2,000 came from? Bust out your calculators and you'll be okay with it in like 5 seconds, okay? So if I do a reciprocal of both these sides, then my inequality switches around. No problem. Now, there's no way to explicitly solve for n. We cannot do it here. We're not going to do it here. So just start thinking about this. Start plugging in some numbers. Tell me something. If I plug in 2, all I need is for this to be more than 2,000. Does that make sense? If this is more than 2,000, then this will be less than 0.0005. Then our error will be less than 0.0005. Actually, it should be way less than that. But this is the idea. So, how about 1? If I plug in n equals 1, is that enough?
No.
Because that's 2 factorial. If I plug in 2, is that enough?
No.
That's 3 factorial. That would be 6. 6, not more than 2,000. If I plug in 3,
No.
that would be 4 factorial. 4 factorial is 24, isn't it? I think so.
4 times 3.
Yeah, 6 times.
Okay. So is that more than 2,000? No. How about 5, I plug in 5. Watch your foot.
120 now.
Say what now?
120 now.
That's not big enough. How about 6? I'm plugging 6.
720.
720. If I plug in 6, remember, if I plug in 6, I'm adding 1 to it.
7.
Oh.
If I plug in 5, okay, let me start again, I got distracted. So if I plug in 5, 5 plus 1 would give me 6. How much is 6 factorial?
720.
That's 720, that's not more than 2,000. Let's plug in 6. If I plug in n equals 6, I get 6 plus 1 is 7. 7 factorial is,
5,040.
is that more than 2,000?
Yes.
So the first term that satisfies this for me is n equals 6. Does that make sense to you? Okay. Now what we do with that, we say this. If I take and add, well, I'm going to add and subtract because it's alternating series. If I take and add the first 6 terms, that partial sum will be within, way within, in this case, way within 5/10,000ths of the actual sum. So what we're going to do, we're going to find S sub 6. We're going to find S sub 6. S sub 6 just says add the first 6 terms. What did we start with anyway? I forgot what my series is. What's it going to look like, S sub 6? Remember, we start at 0, so let's do that. No, I'll start at once.
1.
First one's going to be 1, that's right. If I start at 0, I get 1. Next, I'm going to get a minus, and then I'm going to get a plus, and then I'm going to get a minus, and then I'm going to get a plus, and so forth and so on. Let's plug in 1. Remember, we start at 0 here. So we start at 0. Now we plug in 1. When I plug in 1, what do I get?
1.
Yeah. I plug in 2. I get
1 over factorial 2.
I plug in 3. I get 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial. I ran out of room. Are we okay with all that? Show of hands if you feel all right with that. Okay, so let's figure out what it is. This is 1 minus 1 plus 1/2 minus 1/6 plus 1/12. Sorry, 1/24. Minus 1 over 120 plus 1 over 700. Is that a 720?
Yes.
You can really kind of see the error taking place right now. Check this out. Do you see how, firstly, are you okay getting that far? Make sure I got it right too. Did I get it right?
Yes.
Hope I did. Do you see how small these fractions are getting?
Mhm.
The next one's going to be really, really small. 1 over 5,000 something. Right? Really small. And I'm going to be subtracting it. Well, that's not taking away very much. And after that, I'm going to add, but I'm not adding very much. It's not going to change that much. So here's what we know. If I do this on your calculator or whatever, what I'm going to get, I'm going to do the math for you, but maybe you can double check this. I get 0.368. Did you get 0.368 if you add that? Okay. Let me get a double check here real quick. Did you get the same thing? Okay, just to make sure that my math was right as well. So here's what we know. Let's put everything together right now, okay? Here's what we know. S sub 6 was this, correct? That works down to this partial sum. The sum of the first 6 terms, originally 7 terms because we had the S sub 0 terms, so the first 7 terms, n was 6. So you still got to go by whatever your series says, all right? Add the first, however many it takes to get up to n equals 6 in this case. Here's what I know. Is this equal to S? Is this equal to S?
Tolerance.
Is it equal to S?
No.
No. Is it a good approximation for S?
Yes.
How good? So good that this number is within 5/10,000ths of this. It's that good. And that's how you use the error. Did that make sense to you? That's the idea, folks. Show of hands if you understand the idea, you feel okay with it. Cool.
All right.